In the previous session, we have studied the Coulomb's law in the chapter of electric field and electric charge. We have completed the section of electric charge, and till Coulomb's law the syllabus is over. Now let us continue with the remaining syllabus, that is electric field. It is a common experience when a magnet is placed in the space, and around the magnet there will be a field. That field is called magnetic field. Magnetic field. And any magnetic material like an iron nail is placed in that field, then there is an magnetic force acts on it. A magnetic force acts on it, results in the attraction of this magnetic material towards the magnet. Means this magnetic field interact with this particular magnetic material. That interaction results in a force. That force is called magnetic force. That force is actually on a magnetic material. It is attractive. Suppose another magnet is placed in the field, then if like poles are facing each other, then there is a force of repulsion. And if unlike poles are placed facing each other, then there is a force of attraction. Means magnetic force may be attractive or repulsive in nature. Means around the magnet there is a field. The field is called magnetic field. Similarly, around every body there is a field. That field is called, the body may be a magnetic body or non-magnetic body, or charged body or non-charged body, uncharged body. There is a field called gravitational field. Here is the body, and around the body there is a field in the space. That field is called gravitational field. Gravitational field. And if any other body is placed in the gravitational field of this particular body, then the field of this body, the gravitational field of this body interacts with this body, results in a force. That force is called gravitational force. Because of this gravitational force, this body will be attracted. The second body will be attracted by the first body. Okay. Similarly, this body number 2 also will have its own gravitational field, and this field of this body interacts with the body 1, means interacts with the field of the body 1, results in a force. That force is also gravitational force. At the same, it means the body 1 also, the body 2 also attracts the body 1 towards it. So means around the body, around any body, there is a field. That field is called a gravitational field. Similarly, if there is a charge, then around the charge in the space there is a field. That field is called electric field. Suppose the charge is at rest, the field is called electrostatic field. Static means at rest. If the charge is in motion, then also there is the electric field exists around that moving charge. So, but time being, in this section, let us consider only the electric field due to a static charge. Means charge is at rest. That field is clearly called as electrostatic field. But simply I will call it as, hence onwards we will call it as electric field. If the charge is at rest, it is especially the field generated around it is called electrostatic field or simply electric field. Okay. Now let us in detail study the electric field. Okay. In this particular section in science, let us study the properties of electric field and its effect, etc. Let us study hence onwards all those things. Consider, so write down the notes, whatever things are I am writing on the board, not a scratching writing, rough writing. So in neatly I am trying to write the notes neatly because my handwriting is not Some things I am scratching on the board, so that is not in notes. That is for simply for explanation, and something I am writing at the corner or somewhere. So that is not in notes actually. So something I am writing neatly, that itself is the notes. You have to write down the notes. Okay. Suppose a charge, suppose a point charge Q. So what do you mean by point charge? Already it is explained. Suppose two charges are there, Q1 and Q2. The electrostatic force between those two charges is 1 upon 4 pi. The electric force F is equals to 1 upon Coulomb's law, 1 upon 4 pi epsilon. F is equals to 1 upon 4 pi epsilon Q1 into Q2 upon R square bar. R is the distance between the charges Q1 and Q2. So this is the magnitude of what? The magnitude of the electric force between the two charges Q1 and Q2. It is already studied. And where Q1 and Q2 are the 2 point charges. What do you mean by point charges? The distance R, where are the distance between the charges, is far large as compared to the dimension of these charges, as compared to the size of those two charges Q1 and Q2. The separation R between the charges is large, then the charges are called as point charges. Point charges does not mean that a charge is stored in a point. The dimension of the charge is negligible as compared to the distance, then the charges are called as point charges. Okay, this is the point I have written in the corner. This is the not a notes to be written in our notebook, but it is simply for explanation. I have written something, so you can understand which one is the notes and which one is the things written for the explanation purpose. Okay, suppose a point charge Q is placed at the origin O, means where the charge is placed, that point is to be taken in the xyz space. In the space is the for reference, the reference frame for the space is xyz coordinate system. No, so the space is in the xyz coordinate system is to be mentioned. In the space, let P is a point. Let P is a point at a distance R from the charge O, from the point O, from the charge Q is placed at the point origin O. The electric field at the point P is defined by E bar, where E bar is the notation for the electric field. The bar indicates arrow mark, E arrow mark, and I am reading it as E bar. Actually, E arrow mark over the head indicates a vector quantity. Okay, A bar is a vector quantity. Okay, A arrow over the head. Okay, E bar is equals to 1 upon 4 pi epsilon naught into Q upon square into R cap. Q upon R square into R cap. Okay. What is this R cap? The electric field at that point is given by E bar is equals to 1 upon 4 pi epsilon naught Q upon R square into R cap. What is this R cap? R cap is a unit vector in the direction of R bar. What is this R bar? The vector OP bar, the vector position vector, OP bar is equals to R. and r cap is a unit vector. R cap is a unit vector in the direction of r1. In the direction of r1. Therefore, r cap is equals to r bar divided by magnitude of r bar. Okay. So this is the vector theory. Unit vector in the direction of a vector, r bar is given by r cap is the unit vector in the direction of r bar, and it is given by r cap is equals to r bar divided by magnitude of r bar. Magnitude means length. Magnitude means length. That's why r bar divided by r. Magnitude of r bar means the length of the vector r bar. The length of the vector is denoted by simply the notation r. Magnitude is simply denoted by r. Simply bar is not there means only the letter representing that physical quantity is there means letter representing that physical quantity which is vector in nature is there means it is simply magnitude of that physical quantity. Bar is there means it is magnitude, r bar means magnitude and plus direction. Simply r means magnitude of that vector. Magnitude means in the geometric meaning it is the length of that particular line segment which represents that vector. Okay. So diagrammatically I will show it. So here it is. Here is the what it is charge q placed at the origin O. Here is the point P which is at a distance r. Say this distance is what? R. This distance is r. And this vector is r bar. This vector is what? R bar. OP is equals to r. Actually, the distance OP is equals to r. The distance OP is equals to r, and the vector OP bar is called the position vector r bar. Why? Which one is called as a position vector? The first year we studied any vector with which heel is initial point in O, origin O, is called as position vector. Every point can be expressed by its position vector. So point P, its position vector is OP bar, and point Q is there. Here is the point Q, here is the origin O, then its position vector is OQ bar. The position vector of that point Q is OQ bar. Suppose there is a point R in the space, then its position vector is OR bar. Suppose there is a point S in the space, its position vector is OS bar. Okay. So OP bar in the position means if the initial point is O, initial point of the vector O, then that vector is called as position vector. Therefore OP bar is equals to R bar, and where R cap is a unit vector in the direction of what? In the direction of R bar. Therefore R cap is equals to, you know that unit vector in the direction of a vector is equals to that vector divided by the magnitude of that vector. It is the first year theory. A cap is equals to A cap is a vector, unit vector, cap means unit vector. The symbol cap indicates unit vector. A cap is equals to A bar divided by magnitude of A bar. Okay, that is the formula to calculate the unit vector. Now this actually, look here, let us explain this particular expression. So field is a vector quantity. Okay, field is a vector quantity, and so it is the field at a point. Just try to understand one particular point here. So always field at a point we are specifying. It means the electric field varies from point to point. Electric field due to a charge around the charge in the space varies from point to point. Therefore electric field at a point, we are calling it as electric field at a point P at a distance r from the charge is given by E bar is equals to 1 upon 4 pi epsilon Q upon r square into r cap. So this 1 upon 4 pi epsilon, so suppose a point charge Q is placed at the origin O in the space, and the space is actually, whenever epsilon is taken, epsilon is absolute permittivity of the free space, vacuum. Therefore placed in the space in vacuum. Okay, in vacuum it is. This formula is given for just to take this point also in vacuum. Okay, so that point charge is placed in the vacuum, actually in the space is placed in the vacuum. So there is no even air also. then the formula for the electric field is E bar is equals to 1 upon 4 pi epsilon Q upon R square into R. Q upon R square into R cap. This is the electric field at a point which is at a distance R from the charge Q. Therefore, the electric field varies from point to point. The electric field varies from point to point. Therefore, we can call it as E of R. We can call it as what? E of R bar. E of R bar, E of R bar indicates the electric field at a point depends upon the distance between the charge and the point. Then it means it depends upon the vector R bar, position vector R bar. It means the electric field is a function of R bar. Therefore, electric field E bar is also denoted by E of R, E bar R bar. E bar R bar means E bar of R bar. It is not E bar into R bar. It means electric field depends upon the distance between the electric field at a point depends upon the distance between the charge and the point. Electric field at a point depends upon the charge and the distance between the point. From point to point, the electric field varies. Therefore, the electric field at a point is the function of the position vector of that point R bar. Therefore, it is denoted by E bar of R bar. So, it does not mean that E bar into R bar. It is the E bar electric field is the function of R bar, means electric field depends upon the point, means from point to point, the value of the electric field changes. Okay, the electric field changes. So, E bar R bar is equal to 1 upon 4 pi epsilon Q upon R square into R cap. So, actually, this 1 upon 4 pi epsilon naught Q upon R square represents the magnitude of the electric field, and this R cap gives the direction of the electric field. Okay, so just move one point. So, any vector A bar is equals to A into A cap. Okay, where A is the magnitude of that vector A bar, and A cap gives the direction of this particular vector quantity is having both magnitude as well as direction. So, A bar is equals to A means magnitude of this particular vector, magnitude means length, means it has a numerical figure along with the unit. Magnitude means a numerical value along with the units. A cap indicates it is a unit vector whose magnitude is 1, but A cap is, let's say, A cap especially gives the direction of the vector. Okay, therefore, any vector A bar is equals to A into A cap. Similarly, for example, the dipole moment P bar is equals to P into P cap, where P is the magnitude of the dipole moment and P cap is the direction of the dipole moment, like that. So, here E bar is a vector quantity and its magnitude, E bar is an electric field, E bar of R bar is written. R bar of R bar means it is the function of R bar, means the field changes as the point changes. As the point changes, the position of that point changes, then automatically the value of the field changes. Therefore, E bar depends upon the what it is, the position vector of that point. Means as the point changes, simply as the point changes, the value of the field also changes, means electrical field changes. Then electric field E bar of R bar is equals to 1 upon 4 pi epsilon naught. So, what is this epsilon naught? It is the absolute permittivity of the free space, because the charge is kept in the vacuum. It is 1 upon 4 pi epsilon naught. Absolute permittivity of the vacuum is denoted by epsilon naught. 1 upon 4 pi epsilon naught Q by R square into R cap. In the Coulomb's law, so what the value of R epsilon naught is also taken. The value of epsilon naught is 8.854. So, value of epsilon naught is 8. Wait for a minute. Value of epsilon naught is, it is, wait for a minute. It is 8.854 into 10 raised to minus 12 Coulomb square per Newton per meter square. Okay, the absolute permittivity of the free space. So, it is 1 upon 4 pi epsilon naught Q upon R square represents the magnitude of the electric field at that point, where that point is at a distance R from the charge Q. Okay. The magnitude of the electric field is denoted by E. Therefore, E is equals to 1 upon 4 pi epsilon naught into Q by R square. And this R cap gives the direction of the electric field. So, r cap is the direction of the electric field, r cap is in the direction of r bar, and r bar is r cap is calculated by r bar divided by magnitude of r bar. So write down the note here. So one minute. Wait for a minute. I will give the figure. Here is the charge Q at the point O, and here is the point P. Then the OP bar is R bar, and the distance OP is R, and here is the field E bar. Here is the field E bar. E bar is in the direction of E bar is in the direction R cap is in always R cap is in the direction of R bar. Therefore, so now here it is E bar is in the direction of what? R bar. R cap is in the direction of R bar. Therefore, E cap is also in the direction of the vector E bar is also in the direction of what? R bar. So it is R bar is in this direction, and even field at this point P, field at this point P is in the direction of what? R bar. So here is the field. From this point, the field is radially outwards. Okay, the field is radially outwards everywhere. At every point, there is a field. Here it is E bar. Suppose here is the point Q. Say, okay, the position of this point Q is say R. Let us call it as R1 bar. Then the field is what? E bar of R1 bar. It is radially outwards. Here is the point. Let us take it as R. Going to be the charge Q and R. So let us take this point as Q. Sorry, R. The charge is Q. It is placed at the point O, and the distance of that point R from the charge P, Q is R1 say. Then O R bar is the position to R bar is R1 bar. Therefore, the field at this point is E of R1 bar say. E of R1 bar is equals to what? 1 upon 4 pi epsilon Q upon R1 square into R1 cap into R1 cap. Okay. So the field, the direction of the field is in the direction of R cap. R cap is in the direction of actually R bar. So if the charge is Q is positive, then the field is radially outwards. Look here, the field is radially outwards. Here also, the field is radially outwards from the charge, radially outwards from the charge from that point. Okay. Suppose the charge is negative. Look here, the charge is negative. So we draw this diagram. Mind that the field E bar is radially outwards if the charge is positive. Okay. What is the direction of E bar? It is in the direction of R cap. R cap is in the direction of R bar. Therefore, the field is what? Radially outwards. Now, suppose the charge is negative. Suppose the charge is minus Q. Suppose the charge is minus Q, then the field E bar R bar is E bar of R bar is equals to 1 upon 4 pi epsilon naught minus Q upon R square. E bar R bar at the point P is 1 upon 4 pi epsilon naught minus Q upon R square into R cap. Okay, that's equals to E bar R bar is equals to 1 upon 4 pi epsilon naught Q upon R square into minus R cap. This minus is into here into minus R cap. What do you mean by minus R cap? Minus R cap means it is in the direction, opposite direction of R bar. Look here at the diagram. So here it is minus Q. Place there the origin. Here is the point P, which is at a distance R. Okay, and this vector OP bar is R bar. Now, OP bar is R bar. The direction of this E bar is now minus R cap. So therefore, by that one, the field E bar is equals to the magnitude E into R cap. R cap gives the direction actually. R cap gives the direction. So therefore, so here it is minus R cap. So the field E is equals to either what it is, the magnitude of the E bar is equals to magnitude of the field E into R cap. It may be either plus R cap or minus R cap. This minus R cap is in the opposite direction of R bar. R cap is in the direction of R bar. Minus R cap, minus means in the vector, minus means opposite direction. Minus R cap means it is in the opposite direction like this. It is minus R cap. Okay. Therefore, now the field is, electric field is not in the direction of R bar, it is in the opposite direction of R bar. Therefore, the electric field, I will take one more line here. The electric field at that point P is radially inverse. Okay, not radially outwards in this case, it is radially inverse. I will remove this R bar. R bar is understood. So P bar is R bar. So P bar is equal to R. And now, actually the field is not in the direction of R cap, in the direction of minus R cap. Minus R cap is a unit vector in the opposite direction of R bar, therefore minus R cap is in this direction. Therefore field E bar is in this particular direction. E bar of R bar. E bar of R bar means field at a point P whose position vector is R bar. Field at a point P whose position vector OP bar is R bar. E bar of R bar. So field symbol is E bar, but of R bar means the field depends on the point. As the point changes, then the field also changes. E bar is the function of R bar. Just like f of x is equals to x square plus 2x plus 3. It does not mean that f into x is. F is the function of x. Okay. Here also E bar of R bar means E bar is the function of R bar, means as field changes, 3 point changes, then the field also changes. Now 1 upon 4 pi not into minus R cap. Therefore, when the charge is negative, the field is radially inverse. Means it is towards the charge along the line join of the charge in the point. Field at a point, just mind one particular point, electric field, always we are quoting like this, field at a point means the electric field at a particular point we are discussing from, it means from point to point electric field changes, and but one particular point we can use the expression for the electric field, and the electric field is radially inverse means the direction of the field is towards the charge from the point along the line join of the particular radius, along the line join of the charge and the point. That is the meaning of radius. Radially means it is a line join of the charge and the point. Electric field at a point is radially inverse means it is towards the charge along the line join of the charge and the point. Okay. So electric field is radially inverse. Therefore, in R, now let us give one or two notes regarding the electric field due to a point charge which is placed in vacuum at the origin O. Note 1. Electric field is a vector quantity. Is a vector quantity. Note on this diagram. Okay, write on this diagram also. Is a vector quantity. Its direction is the direction of E bar even though it is E bar of R bar, hence let us call it as simply E bar. E bar is radially outwards. Radially outwards if the charge is positive. If the charge is positive. If the charge is negative, full stop. If the charge is negative, then